Topic 8 is looking at acids and bases. There are a lot of sections, so bear with me. So 8.1 is looking at the theories of acids and bases. Early theories of what classifying acids and bases kind of ranged. And so a French chemist called Lavoisier, he proposed that oxygen was the universal acidifying principle because he believed that when anything reacted with oxygen, it created an acid. However, as we started discovering new chemicals, specifically hydrochloric acid, there's no oxygen there, but it had acidic properties. So things get modified as we go through. And then you had the chemist Arrhenius, who created the Arrhenius plot for rates of reactions. He defined an acid could be defined as a substance that dissociates in water to form hydrogen ions and anions. And while a base dissociates into a hydroxide ion and cations, which is actually very close to what it is today, but it was almost too specific, and we needed a much broader theory. And that is what 8.1 focuses on, is that broader theory. So it's called the Bronsted-Lowry theory. There are two separate scientists in two different countries who actually came upon this idea at the same time, and therefore they shared the credit. And it's Bronsted-Lowry. And this is the theory of the proton transfer. And so we're looking at the hydrogens and where the hydrogens are going. And the reason we say it's a proton transfer is when you look at hydrogen, right? So we have hydrogen, and hydrogen has one proton and one electron. And so if you lose that electron and you get an H+, it's called a proton, right? So an acid is a proton donor, and a base is a proton acceptor. So what that looks like is if we have HCl and we have NH3, ammonia, what we expect to happen would be that hydrogen is going to the hydrogen on the hydrochloric acid is going to donate to the ammonia. And acid-base reactions, the majority of them are equilibrium reactions. And so now we get NH4 plus and Cl minus. So there you have your cation and your anion, like Arrhenius explained, but there is no OH minus, but there is a hydrogen transfer. And so that is the theory that is most widely accepted today. So when a reaction occurs with an acid, they create what are called conjugate pairs. So acids will donate that proton to a base. This will not happen if a base is not present. And then vice versa, if a base is not present, the proton doesn't get released, so on and so forth. So a generic equation for what this looks like. If we have HA, so A stands for acid, H is showing that the acid has the H. And we're going to use B for base. This is an equilibrium reaction, and we know that hydrogen is going to get donated to the base, so we get A minus, which is our anion, and HB plus, which is our cation. So here we're going to have pairs. Okay, so we know our A's are going to pair up, and we know our B's are going to pair up. And these are called conjugate acid-base pairs. Because in one direction, this base, the B is a base, and it accepts that hydrogen. But in the opposite direction, that HB plus actually becomes an acid, which donates the hydrogen to become that base. So it's a conjugate acid-base pair. Now we tend to read in the forward direction only. So our HA is our acid, our B is our base. Well, our acid dissociates and gives away that hydrogen ion to create a conjugate base. And the HB accepted a hydrogen proton, which means it has a hydrogen proton to donate back. So that becomes the conjugate acid. You just need to know and be able to recognize acid-base pairs. So if you're given a reaction, look at who has the hydrogen first and who lost the hydrogen to find out what those pairs look like. They have to be the same ions, though. So another example, okay, we have water. And when you put an acid into water, those acids have those floating around hydrogen ions. And water actually works really well to represent an acid base. And you create H3O+. And this is called a hydronium ion. Now, you need to recognize that H plus and H3O plus actually mean the same thing, because when H plus is present, it actually interacts with water, because water has an extra lone pair that will attract those H pluses in the water, and so you get H3O plus, and that is really what the H plus is. So you need to be able to recognize that either H plus as an acid or H3O plus as an acid, right? So if we go look through and look, this H plus is our acid. It has been given by hydrochloric acid, whatever it happens to be, okay? So it's in an aqueous solution. And it gets hydrated and creates our conjugate acid. And so our conjugate acid pairs up with our conjugate base. And so it depends on the direction you look at. So this is our acid because it has that extra proton to donate and release back into that aqueous solution. All right, we're going to talk about water more often, but I wanted to make sure you understood that H3O plus and H plus are the same things. Another example. Okay, so we have CH3COOH plus H2O gives us CH3COO minus and H3O plus. Identify the pairs. So who has that H, and so you look on both sides, who has the H and then who loses it. So here we have CH3COOH. Here it lost its H. So here we have our acid, and then we have our conjugate base. Then water is the base that is accepting that hydrogen ion. And that's all you have to do. Okay, but make sure that you're noticing that the pairs are always going to be the same two compounds. They're just going to be one in ion form and one in a non-ion form. Lastly, is something called amphoteric or amphiprotic. And this is where one compound can be an acid or a base depending on the situation it's in. And water is a notorious amphiprotic, amphoteric compound. And it all depends on the type of reaction that that amphoteric compound is in. So we're going to look at two reactions with water to show you how water can change depending on the reaction it's in. So if we have CH3, we just did that one. If we have NH3 plus H2O, that's going to make NH4 plus and OH minus. So we need to identify where did the hydrogen come from, right? So who lost that hydrogen? Well, here we have water, and it becomes an anion, which means it lost a proton. So at this point, water becomes our acid, and hydroxide is our conjugate base, which means NH3 was our base, and NH4 plus became a conjugate acid. So in this instance, water is acting as an acid. Another example is if you take HCO3, which is a dissociated form of carbonic acid, react that with water. You get CO3 minus and H3O plus. All right, so who lost that hydrogen? Well, HCO3 lost that hydrogen. So here you have your acid and your conjugate base. Water accepted that hydrogen, so that was our base, making our conjugate acid. So these are two situations where water could go either direction. Now, just keep in mind, this can happen with anything that has multiple hydrogens, so it either can accept and or donate because it has the ability to hold multiple hydrogens. So some common compounds that can be amphoteric: H2O, H2CO3, H2SO4, H3PO4, so on and so forth. Because as these guys become ions, they have the ability to accept and or donate hydrogens because they have multiple hydrogens in which to work with. Overall summary on Bronsted-Lowry. So Bronsted-Lowry acid is the compound that has the hydrogen to donate. So it dissociates in an aqueous solution and releases that hydrogen into that solution. The Bronsted-Lowry base has the ability to accept the hydrogen. Reason usually is it's got a lone pair. So if it has a lone pair of electrons, it has the ability to take on an additional positive ion. And that's all for 8.1.